Hi everyone, thanks for coming. I'm very happy to be able to introduce Keith Dienes. He's faculty at Arizona, as we just heard, but also does all of us a fantastic service with his work at the NSF as a program director. And aside from just being happy to see Keith, I'm also very excited to hear what he is telling us about today. The past couple, well, in my point of view, for the past couple of decades, Keith's been pursuing this really interesting program, which is one of the most novel and yet also most well-motivated approaches to understanding the fine-tuning problems of particle physics. It seems like he's made some enormous progress recently that I'm very excited to hear about. So Keith, whenever you're ready, you can take it away.
All right. Well, it's a pleasure to be here. I'm guessing you can all hear me, and I'm going to share my screen now and put it in full screen mode. So hopefully you can all see it there.
Yes.
So the genesis of this talk was actually when Seth came to here, the University of Maryland, and gave a seminar. And at one point I stopped him right in the middle and I said, right there, why don't you make a symmetry out of that? And I was realizing afterwards that this is a very nice way to introduce the Royal Road into string theory. So that's what I'm going to be talking about today. UPI are mixing and effective field theories and how you can use them and to understand in a rigorous way how to calculate the Higgs mass in string theory, which surprisingly is something that people have not really done. So this is work done in collaboration with Steve Abel, who is he's faculty at the IPPP in Durham in England. And this is a very long paper which appeared on the archive last summer. And it's based on a long line, as Seth was saying, of earlier work that I've done in this field. So, and it'll all be wrapped up together in one package, I hope. So let me just start by saying that this is a talk about string phenomenology, which of course is the aim of extracting low energy phenomenological predictions from string theory, but we're not going to do this in the usual way. If you look at a string phenomenology paper, you download it, usually what they do is they start with some vacuum or a string model. I'll use these words interchangeably.
Otherwise, question already. Sorry, Keith.
The question is about the microphone. Keith, what microphone are you using? Because you're kind of cutting in and out a little bit. It's a little.
I'm using my laptop microphone, and I don't have the power or knowledge how to change that.
Ah, okay. Okay. For some reason, it's kind of cutting in and out a little bit.
Almost sounded like
there's some feedback.
Maybe
from our side.
Let's try feedback on this thing.
and see what's.
Let me check if anyone else has a.
If everybody, maybe everybody else can mute. Does that help? It's cleaner on my end now. All right. Of course, I'm not hearing you. I'm going to continue unless you signal. Okay. So the traditional approach to string phenomena. Now, if you want to interrupt, have a question, do interrupt. Just feel free. I can't see everybody on my screen. You know how it is to give these talks. But if you have a question, feel free to interrupt. So the traditional approach to string phenomenology is you start with some string vacuum or some string model. Otherwise, if you didn't do that, you'd be limited to making generic statements that might hold across certain classes of vacuum, but not specific things, specific numbers. Within that vacuum, you would then enumerate the massless states that arose in those models. You would then construct a field-theoretic Lagrangian that describes the dynamics of those states. And then you would analyze that Lagrangian using all the regular tools of quantum field theory without further regard for the origins of those states within a string theory. And this treatment may be okay for certain purposes, but calculations performed that way, I think, have a serious shortcoming. And I've been kind of saying this for many years, which is that by disregarding the infinite towers of states that necessarily accompany those low-lying modes within the full string theory, these calculations disregard, they essentially throw out the stringiness. Many of the, in particular, underlying string symmetries that ultimately endow string theory with a plethora of remarkable properties that go beyond our field-theoretic expectations. Now, these states are usually at the Planck scale or at the scales associated with a compactification geometry, so you might wonder how they could ever play an important role for low-energy phenomenology. You would ask, why can't you just integrate them out? that would leave behind higher dimensional operators suppressed by powers of those scales. Would that justify the usual treatment? And the answer is that there are a lot of reasons why you might be cautious about that. For one thing, we wouldn't be integrating out 1 or 2 or 3 heavy states. We'd be integrating out an infinite tower of them. And even more severely, those towers of states have degeneracies that grow exponentially. The number of states at each level grows exponentially with their masses. This is the Hagedorn phenomenon. So you might wonder if that can still leave behind just a power law suppression of higher dimensional operators. No, I don't think anybody's really proven this or studied this in any detail. It's also natural to expect that infinite towers of states would affect particularly quantities such as the Higgs mass and the cosmological constant, which are positive mass dimension and are therefore sensitive to all mass scales in the theory. And moreover, many of the string symmetries that rely on these infinite towers of states transcend what you can easily incorporate within an EFT framework. For example, strongly coupling dualities intrinsically rely on those full towers. Or for example, even within the purely weak coupling regime, T-duality. Very classic stuff. The physics of closed strings compactified on a small compactification volume is indistinguishable from the physics associated with strings compactified on a large compactification volume. So this suggests immediately some sort of stringy equivalence between UV and IR physics. This has been known since almost 35 years, actually. And so you could ask, how can you incorporate these kinds of symmetries within an EFT approach in which you integrate out heavy states while treating light states as dynamical? And you might say, well, okay, but strongly coupling duality and T-duality are spacetime symmetries. They're consequences of an underlying worldsheet theory. But closed strings also have another symmetry of this sort, which must be imposed for consistency directly on the worldsheet. And this is worldsheet modular invariance. And this is what I'm going to be talking about in this talk. And don't worry if you don't know what it is. I will introduce it very slowly for field theorists. And this will be the focus, but this is critical. This lies at the heart of many of the finiteness properties for which string theory is famous. It is an exact symmetry of all perturbative closed string vacua, which means that for any string theory, this symmetry provides tight constraints on the spectrum of string states at all mass scales and their interactions. And it's preserved, therefore, even as string theory passes through phase transitions. So you can consider this the ultimate UV-IR mixer. It enforces a delicate balancing between low and high scale physics. Now, a lot of phenomenological questions you might want to ask about the universe are not likely to depend on such symmetries. That's certainly true. But I think the presence of such symmetries is likely to be critical for addressing fundamental questions which are connected with finiteness or the stability or even the coexistence of different scales under radiative corrections, such as hierarchy problems, chief among them, the Higgs mass and the cosmological constant. So if we're to take string theory literally as a theory of physics, we should really be performing our calculations within this full framework of string theory, incorporating all of the relevant symmetries and infinite towers of states that string theory gives. So in this talk, what I'm going to do, at least in the second half of the talk, is provide a calculation, such a calculation of the one loop Higgs mass. Now, I want to say I have no political agenda here. I'm just doing a straightforward string theory calculation and see what comes out. And surprisingly, this has not ever been done before, at least not in a way that I think respects modular invariance. We will not choose a particular string model. Our goal, therefore, is to establish a framework for doing this calculation rigorously, which takes into account all string states and uses only techniques that preserve modular invariance. One could then apply our framework within your favorite string model. You could then go off and do this in your model. Our goal will be to see how the results agree with EFT-based expectations and also where they differ. And I just want to say, we're not attempting to solve any hierarchy problems here, but we will see some intriguing ideas at the end emerging from these kinds of analyses. Let me say, it's hard to give a talk on string phenomenology because you have competing interests. You want the string theorists in the audience, and there are certainly here many. You want them to understand it, but there are also field theorists in the audience, and you want them to understand it. And many of the ideas are familiar to string theorists, but utterly alien to field theorists. So I'm going to try to walk a tightrope here. I'm going to start with field theory, and I'm going to try to reformulate field theory in a way that makes our later string results plausible. String theorists will immediately know what I'm doing. They're going to recognize it and smile to themselves and say, oh, he's doing that. Okay, let it go. I'll then provide the full string results, many of which are new, and I will interpret them in terms of field theory. But I want to say right now, the full string calculations are messy. I'm not going to go through them. They're not particularly illuminating. I'll skip them and I'll just quote the results, but all the details are in a very long paper here, and that includes 2 nasty appendices, which are there as well. Okay, so let's...
Keith,
yeah.
maybe I'll just be smiling in a few minutes as you
will.
were anticipating.
You
But
will.
I just have a general question, which is, how do you even know what the Higgs is in a model independent way?
Very
I
good.
mean, if you
I'll
don't know
get
what
to
the
it.
gauge group is and the content is, how can you identify the Higgs?
Very good. Let me, when I finally, at about 80 slides, so, okay, now let's use this for the Higgs. That'll be right where I address that question. So,
Okay,
hey, it'll come there.
all right.
Okay, so let's start the story by examining the one loop. This is for field theorists. String theorists will know this. One loop, Coleman-Weinberg, if you will, effective potential in string theory, the simple vacuum bubble. Normally, it's given by this expression. This is the number of, G sub n is the number of states, bosons minus fermions. Always, we're always going to have a boson minus fermion kind of count, a graded counting. And this is the summation over the spectrum of the cosmological constant or of the theory. And this is going to be our effective potential. Now, it turns out that the best way to connect field theory to string theory is to reformulate string theory in a way that is not typically taught very much, which is called the Schwinger world line formalism. This is pure field theory, but it's the road to string theory. It's a purely field-theoretic formalism. Basically, what you do is you calculate the amplitude for a particle to move from, let's say, x to y within a fixed proper time. You hold that fixed. This is the Schwinger proper time. And in some sense, t is the total length of the world line around the bubble. And then you calculate the total propagator by integrating that amplitude over all proper times that it takes. Mathematically, it just corresponds to taking this expression and using a certain identity to replace this log and put it up in the exponential in terms of this Schwinger proper time. So if you do that, you get that the same vacuum energy is now written like this. And this is just the Schwinger proper time formulation of the field theory. This is just field theory. I'm now going to just do a bunch of standard manipulations. I'm going to perform my P integrations. I'll work in an arbitrary space-time dimensionality D. I'll recognize that this dimension, this Schwinger proper time has a dimension of mass dimension of -2. So I'm going to make it dimensionless. I'm going to pull out a new quantity. Instead of T, I'm going to scale out an arbitrary scale mu. And this is going to be, I'm going to call it T2 hat, if you wish. This is my dimensionless Schwinger proper time. The mu comes in front, it becomes an overall scale, everything else is dimensionless. My remaining T integration is now expressed in terms of this dimensionless T2. There's a prefactor, which came from the prefactor. And then there's this sum over states with what looks like a Boltzmann suppression. This looks like a Boltzmann suppression, but you would say, therefore, this is like a partition function, but it has a -1 to the F grading. But we're going to call this the partition function. And I'm going to define this quantity to be Z or Z right here. So I've now recast the result in terms of some overall dimensionful quantity and an integral over this dimensionless Schwinger proper time from 0 to infinity with a partition function that looks like that. Okay. All right. So this is what we have. This is just another way of expressing the standard field theory result. And I integrate from T2 equals 0 to T2 up to infinity. All right, I'm now going to do something completely unmotivated, but there's nothing wrong with it. I'm going to introduce a dummy variable T1, and I'm just going to integrate it from -1/2 to +1/2. I'm not going to put T1 anywhere else, so this is just another way of writing 1. But it means that my region of integration now goes from -1/2 to +1/2 in a T1 direction, a dummy direction, and a T2 direction, which is the Schwinger proper time. And so I'm now going to integrate over this entire strip. I've done nothing. I've introduced a dummy X direction here, this horizontal direction that contains no information in field theory. It's a dummy variable. This is called the strip. And I, therefore, in ordinary quantum field theory, this is what I would do. I would take my vacuum potential is just this quantity, the partition function of the theory, integrated this way over the strip from -1/2 to +1/2 up to infinity, where the partition function is just the sum over the states, each suppressed by their mass. All right, divergences. Well, as is typical for the Schwinger proper time, as T2 goes to infinity, this is the IR direction, because as T2 goes to infinity, the only states which survive this process are the very light ones. This is the IR direction, the lightest states dominate. The other direction, as we come down to here, is the UV direction, as T2 goes to 0. These are where all the states contribute equally, so you're sensitive to how the accumulation of infinitely many states in the theory, if you have any, is contributing here. So the IR up here, UV down there. And how would you handle divergences if there are any divergences in this theory? You would put in a cutoff. And you would put in an IR cutoff here or a UV cutoff down there. This is one very natural way to do it in field theory. And you would introduce these as needed. And this introduces new mass scales. Okay, standard field theory. Now, so far we've stayed within traditional quantum field theory, but I want to ask a hypothetical question. What would happen? Still a field theory question. I'm only thinking as a field theorist. What would happen if our theory had an exact symmetry under T to 1 over T? We'll discuss why on earth this would be relevant, but let's just ask, what if it did? Well, such a symmetry is clearly not field theoretic, but let's pursue it anyway. What effects would it have? How could we interpret it? Well, back to this again. The strip would be invariant under T2 goes to 1 over T2. That would just flip us across the T2 to 1 over T2, the T2 equals 1 line. The measure is invariant. So the partition function would also have to be invariant. That's what I'm suggesting in order to have this symmetry. Okay, so that's what it would mean. It would also mean then that the physics from the upper region of the strip, let's call it S1, would have to be equal to the physics, same physics, as from S2, which means that S1 and S2, the integrations over these separate regions, provide redundant descriptions of the same physics. Which means that if there's a UV divergence down here along T2 equals 0, that must be the same as the IR divergence up here at T2 goes to infinity. Otherwise, and they would be attributable to the same physics because they are symmetric, because there is this symmetry. Due to the redundancy, the total integral over the whole strip would now be written, would be understood as twice the integral of the contribution from either S1 or S2 alone. And the factor of 2 reflects the number of identical copies that make up of this either region that make up the strip. In other words, S2 would nothing be but the image of S1 under the action of the symmetry. Or likewise, S1 would be the image of S2. All right, this should sound familiar. There are two analogs of this that we already know. The redundancy of description that we would then have is like a gauge symmetry. And integrating over both S1 and S2 would be like integrating over all the gauge slices. Of course, in this case, there are only 2 gauge slices. We know that. The overall factor of 2 is in some sense that gauge volume. But the appropriate treatment then is still the same. We know we should effectively divide out by the gauge volume by choosing only 1 gauge slice. Another example a lot of people know is by thinking about compactifying on circles. If you would compactify on an extra dimension on a circle, there it is. Then if you mod out by a Z2 symmetry, you construct an orbifold. So what do people who are familiar with extra dimensions, what do? You know that when you do this, the compactification volume of the orbifold is now only half that of the circle. You're effectively compactifying on the resulting line segment, which is the orbifold. And so that's the same idea. So we should do the same thing here. We should fold the strip across this line and consider this to be the region of integration for 1 gauge slice. And now we integrate over S1 and not S2. We've truncated the strip to just 1 slice. This eliminates the spurious factor of 2. And of course, we could have chosen to do it the other way. We could have chosen S2. It's our choice. Let's do S1. Okay, but there's a big implication that has happened here. This folding implies that the bottom part is folded onto the top part. So there's now any longer a unique up or down direction on the remaining segment. There's no notion of an increasingly UV or IR direction because all directionality has been lost. This has become, in some sense, a non-orientable region. The 2 divergences in particular, the one at IR up here and the UV one down here, have been mapped on top of each other. So in this new theory, there's only 1 divergence. You can call it UV or IR according to your choice or convention as to whether you chose to work within S1 as your fundamental region or S2. It's your choice. Okay, now this nightmare only arises if you actually have a T2 to 1 over T2 symmetry. This is not likely to happen in string theory, and you can see that immediately. The strip is invariant, sure. The measure is invariant. But the partition function would also have to be invariant in such a theory, and that's very hard to arrange because that means that this T2 here would become a 1 over T2. Each T2 factor would be inverted in the exponential, but yet you want to say it's a symmetry, so it should come back to itself. So somehow there needs to be some sort of mathematical identity that relates exponentials with inverse T2s to exponentials with positive T2, positive powers of T2. Now, there actually are such things. They're called Poisson resummations. Some of you may know this from condensed matter physics. This is saying sum over sites in a lattice is sum over the sites in the dual lattice. There are lots of these identities that actually relate a positive power T2 to a negative, to 1 over power of T. But this, notice, because of the infinity of sums here, this means that this could only be useful in any possible theory if there were an infinite tower of states. And that's rather sick from a field theoretic perspective. You would also have to have a very tight balancing of masses and degeneracies at each level in order for such identities to even have a chance of applying. So this is what you would have to do to even have a symmetry like that. But let's turn to string theory. Now, what actually happens in string theory? Now, a warning, in this talk, I'm going to be focusing on closed perturbative strings. Now, that's a huge class. It includes type 2 strings, as well as heterotic strings formulated in any number of spacetime dimensions with any spacetime compactification manifold or orbifold, with or without spacetime SUSY. I'm being completely general. We will be for the whole talk. No restrictions on particle content, gauge symmetries, etc. The only hidden assumption I'm going to make is that the theory doesn't have tachyons, because otherwise it's sick for deeper reasons. So we'll assume there aren't any physical tachyons. Okay. Now, we don't have to know a lot of string theory, but let me, for the field theorist, just make some very simple statements. World sheets become world lines become world sheets because our point particle becomes a one-dimensional string, so a one-dimensional world line becomes a two-dimensional world sheet. Different excitations or configurations or vibrational modes of the world sheet correspond to different particles in space-time. There are different kinds of excitations, oscillator modes, KK modes, winding modes, not important for our purposes. The thing that is important, though, is that anytime you excite a mode on that string world sheet, it's like a wave on that world sheet, and it can propagate either clockwise or counterclockwise as the thing propagates. So these are called left-moving and right-moving modes, and the total mass in space-time of the state has separate contributions from the excitations of the left-moving modes and from the right-moving modes. So in string theory, there's left and right-moving contributions, and they add together to make the total mass. And because of these oscillator states, the total number of ways of configuring these excitations actually grows exponentially with mass. That's that Hagedorn phenomenon. That's all you need to know. So how do you calculate a one-loop amplitude like that in string theory? Well, this is what we had in field theory. The Schwinger proper time described the length of the circle around the cycle. We then integrated over all t. Well, now this is going to puff out and become a torus. And this t, the length, well, there are two ways it could generalize. It could become the volume of this, or it could become the shape of this. Volume and shape are the same for this one-dimensional thing, but for two dimensionals or higher, they are different. And it turns out it generalizes to the shape. So what we want to do is then integrate over all possible shapes of torus without overcounting. Shapes, not volumes. We don't care if we rescale the whole thing. That's okay. But whether it's long and skinny or big and puffy, that's what we care about. That's the shape. So how do we describe the shape mathematically? Well, we know that what is a torus? It has two cycles. It has two boundary conditions. If we go around the y, let's suppose we have y1 and y2 are the coordinates on this sheet, on the torus. We can go around the y1 direction with a radius r1, or we can go around our second direction with a radius r2 and come back to themselves. These are invariances. These are cycles. So if we go around r1, we come back to ourselves. So this is identified with this, or likewise this with this. The only difference is I'm introducing an angle theta. All this says is that for one of the directions, I'm just going to choose one of the directions to be the orthogonal direction, if you will. So you come back to where you were on y2 if you go around this much on y1. But if you go around on y2, on the other hand, you don't come back to just y1. You also come back with a little shift. And that's the idea, and that's why there's an angle here. So as you go around, you come back with a shift. All right, that's the general thing. So in general, three real parameters, R1, R2, and this theta, describe the two cycles of the torus. They tell you what torus you're on. And we would like to have a nice way to describe that. So we're going to imagine this is like a complex plane, just this y2, y1 coordinate space. We'll normalize this to 1, because we don't care about the volume. We're going to rescale the whole thing. And then wherever this lands, it's going to be some point in the upper half plane, and that's a complex number tau, and it's the ratio R2 over R1 e to the theta. This is going to be our complex number, which describes the shape, tau. And there's one more, that's one complex number that absorbs two of these real ones. The third thing is that volume that we don't care about. Okay, so therefore, any torus can be described through a complex number tau by specifying a complex number tau in the upper half plane. Now, of course, as I go around and around, recurring cycles of the torus map out a lattice in the plane. So if there's my 1 and my tau, then I fill out a whole lattice. The question is there any redundancy in this description? In particular, are there any cases where different values of tau will give the same fundamental cell? Well, you can see one already. If I have tau, tau plus 1 is going to describe the same lattice. So if I have any torus described by tau, another way I could describe the same torus is tau plus 1. And tau plus 2 and tau plus 3, I could repeat this. But there are yet other things I could do. For example, what if I went to minus 1 over tau? Remember, tau is a complex number. This turns out to give me what looks like a different lattice, but actually it's the same lattice, only rotated. And so that means that I can also say that minus 1 over tau is in that class. But that means I can now combine these things. I could do a tau plus 1 shift, and then I can do the 1 over tau shift and then add 1 by using this, and that would also be in the same class. And minus 1 over tau plus 2, and that would be in the same class. Or I could do the shift first, tau plus 1, and then do the minus 1 over it. Or minus 1 over tau plus 2, or I could do the shift and then the inversion and then the shift. And you get the idea. There's an infinite number of ways I could combine, all of which are equivalent. So this exponentiates up in general into any mapping. Tau goes to any of these possibilities where A, B, C, and D are integers, and where the determinant AD minus BC, if you looked at this like a matrix, the determinant is 1. So this is called the modular group. For any tau, all possibilities like this also describe the same torus. So the modular group describes the tau redundancies inherent in describing tori. Tori are unchanged. They're conformally equivalent, the same shape, if I map tau to tau like that. This is an infinite dimensional group, obviously. We're going to call it gamma. It turns out then that all elements of gamma can be generated as sequences of two fundamental generators. The first one that does the shift, the second one that does the inversion, T and S they're called. So I had these classes of equivalence, all these were the same. Well, yeah, this is when I act with T, that's there, T squared, that's there, S, that's there, or I first act with S and then T, that's this, and so forth, all there. So an important subgroup of this is the subgroup just generated by 1 and T alone. No inversions, just this. So what then is the description? The upper half plane describes all possible tori, but the redundancy group describes the inequivalent ones. So it's just like a gauge theory redundancy, just like before. So what then is the subregion? Like when I folded the strip to just S1 or S2, the upper half or the lower half, I want to ask the same question. What is the subregion that captures just one copy of each torus without overcounting? We're going to call that one gauge slice. Well, we can imagine it. We start with the upper complex half plane, and now I can mod out by the generator. That just puts me onto the strip from minus a half to plus a half, because the next strip from a half to 3 halves, that's just the T version of this, so that's redundant. And then the next thing I want to do is somehow get that inversion symmetry. Tau goes to minus 1 over tau. That maps anything with a modulus tau, mod tau to 1 over that. So I just want to choose anything where the modulus is bigger than 1 or smaller than 1. I'll choose bigger than 1. So that becomes the fundamental domain of the modular group. Anything in here is conformally inequivalent. Everywhere else in the upper half plane is equivalent by the modular group, by the symmetries. Now, this last step of going from that strip to the fundamental domain actually is very important. This looks like field theory. Remember, this is the strip that we had. This is the fundamental domain of the subgroup that was generated by T alone, because we had not yet implemented the S transformation, the inversion. This is what I'm telling you is string-theoretic. It's just this shape as F, and the fundamental domain, therefore, of the full modular group generated by S and T both, not just S, not just T alone. So the question is then, how many gauge slices do we have when we go from here to here? How many copies of F are there within S? Well, the answer is, in the previous case with 1 over t to 1 over t, the answer was 2, but the answer now is the dimensionality of the coset, the full modular group divided by just the ones generated by t alone. And the answer is that it's an infinite number. There are an infinite number of these that make up that. Let me show you them. Sorry that I couldn't get all the colors to work. I'm hand tracing this, if you could believe it. I'm not that good. But here's that fundamental domain F. And I'm saying that there's an infinite number of their images under the modular group that comprises this strip. So if I take this yellow region, and I do tau to -1 over tau, S on it, I get this purple region, lavender. If I instead do T, I bring it over to here, and then S, and I get this one. If I go T to the -1 and then S, I get this one. And all different possible combinations will lead me to all different maps of it. Each one of these, this green one here, this red one here, are just different images of the same F. And there are an infinite number of them as you get down in there. It almost gets like a fractal. And each domain is an equally valid choice. I could decide to work on string theory in this choice, or this gauge slice, or that one, or any one. But we're usually going to choose this one up here. So together, these completely fill the strip, but each domain has a unique UV or IR cusp. Now, we're not used to thinking of the upper limit here as tau 2 goes to infinity as a cusp. But really, when you're infinitely far away, this little 1/2 to -1/2 region, you could think of it as infinitely tiny compared to the big distance. So this projects to just a single cusp point. And when you map it under any of these others, it comes to a cusp. You see, every one of these other regions has a cusp. So it's either got a UV point down here like these, or an IR point up there. Now, these shapes are weird looking until you look at it just by extending it out just to see what it looks like, and you see that it's just lines and circles. That's all this is. And there's a reason for that, because this is a linear fractional transformation, and linear fractional transformations in the complex plane map lines and circles to lines and circles. That's what they do. But this is very important. Now, this is the modular group. Now, people who are used to modular symmetries know all this intimately. You might be used to another kind of modular, which is modular furniture. But indeed, this can be used to give a whole new meaning to the phrase modular furniture. Some mathematician in Switzerland, or I think he's actually from New Zealand, created this, the modular cabinet. I think you can order it online. There you see exactly what I was talking about, the fundamental domains and so forth. You can look it up online. So in string theory, we are instructed to do something really hard to do, but we have to do it, to fold the strip into F. You take each one, you make a little fold, a little fold, a little fold, I don't know, and you keep folding it until finally you build just this shape. This requires an infinite number of folds. Once all the folding is done, all the cusps lie on top of each other up at I infinity. So what we had in field theory, which was an expression that looked like this, where you took your integration over a strip, you now integrate over a fundamental domain in string theory. So the unknown scale mu becomes the string scale. The strip becomes the fundamental domain. The T2 and T1 now just become the imaginary parts of tau, the complex number, which you can call tau1 and tau2. The partition function before just cared about the field theory mass. That's all there was. But in string theory, we have a mass left and a mass right. And as I told you, tau2 is the field theory kind of direction. It just cares about the total mass. But there's another factor, tau1, which cares about the difference of the masses. This is a purely stringy thing. This tau1 direction now has a meaning. Here it was a dummy variable. Here it carries string meaning about the difference between left and right movings. So states that differ by this are not field theoretic. They're weird stringy things. They're called physical if this is vanishing, if those are equal, they're level matched, m left equals m right. They're called physical or level matched. They're like on shell, and they have field theory limits, and their analogs are therefore they are T1 independent, tau1 independent. That's why they look like field theory. Other ones, these other states have no field theory analogs. They contribute in loop amplitudes as off-shell virtual states from the curved region. Basically, if I imagine integrating across tau 1 from -1/2 to +1/2, if I'm doing the integral here over the fundamental domain, anything where this is not satisfied would not contribute. But if I don't get to integrate all the way across, such as down in this curved region, then it does contribute. And that's why these are stringy things that don't appear in field theory. Okay, now I want to stress, modular invariance has compelled this structure. I didn't put it in. It's unavoidable. It's nothing more than the symmetry group reflecting the invariances of tori. And it's therefore has to be baked into string theory from the beginning. This is not some add-on. And it ensures that string theory is consistent, in particular that it has consistent one-loop diagrams. It's part of reparameterization of variance. The physics cannot depend on how I chose coordinates on the world sheet. And at the level of tori, that's what this means. Sometimes people call this a one-loop symmetry, and I've discovered that field theorists interpret that completely incorrectly. So I want to say modular invariance is sometimes called a one-loop symmetry because it ensures the consistency of one-loop diagrams, but the terminology is misleading. It's not a symmetry that's violated at higher orders. It's an exact symmetry of the partition function, and therefore of the entire string spectrum of states and their interactions. You can't break modular invariance by small amounts or through interactions, just as you can't break the ward identities associated with gauge invariance through gauge invariant interactions. This doesn't happen. So if you're staying within string theory and string theory truly governs all your interactions, then even phenomena such as phase transitions could deform the theory and change its degrees of freedom, but only within the space of modular invariant theories from one such to another. So are there higher loop diagrams? There are. Do they introduce additional redundancies? It turns out the answer is no. Within certain closed string theories, you can prove from amplitude factorization and physically sensible state projections that one-loop modular invariance automatically implies multi-loop modular invariance. This was shown years ago by Kawai and Tai in certain cases. And so in those kinds of cases, which are pretty general, one-loop modular invariance is sufficient. Okay, but the consequences of this folding from S into F are profound. First are the consequences that look like what we had in field theory. The lower portions are folded into the upper portions in F. And so there's no longer a unique up or down direction. There's no notion of an increasingly UV or IR direction. There's only one possible divergence, therefore. You can call it UV or IR, depending on whether you choose to work in F or SF or any of these others. It's your choice, just as we saw in field theory, if I did this weird map. But there's something else. There's an additional feature because unlike the field theory case of this, infinitely many foldings are required. So we're dividing by an infinite gauge volume. Or equivalently, an infinite number of field theory divergences are eliminated, leaving only a single string divergence. So modular invariance not only relates UV and IR divergences to each other, but also softens them since we're dividing out by the infinite number of copies. Essentially, some of the divergences of field theory are reinterpreted as a spurious gauge volume in string theory, and therefore eliminated. This is why string theory is more finite. So if you invert this procedure, you could imagine that each string divergence would unfold into what would appear to be a combination of UV and IR divergences in field theory. So you might have a divergence in string theory. In the F representation, you would call it IR. In the SF representation, you would call it UV. Either way, it's the same thing. That's string theory. But it would unfold into a combination of UV and IR, a modular invariant combination in field theory on the strip. But it would do this an infinite number of times. So each of these divergences, you have to divide by the coset, the infinity. And so this is the mapping between UV and IR physics between string theory and field theory. Now, you could consider, for example, the cosmological constant in string theory and see what happens. So let's actually do that. The tree level contribution actually vanishes by conformal invariance in string theory. So the leading contribution to the cosmological constant is actually this quantity right here that we've been talking about all along. And here it is. So in the F representation, the only possible divergence is IR, as we said, from the T2 to tau2 to infinity region. And these divergences, as tau2 goes to infinity, are governed by the lightest states. Now, there is a theorem, which I proved back in 1990, that there are always certain kinds of tachyonic states in the theory, but they're not level matched. They don't make any contribution up there. And matched states also don't lead to divergences. And so it turns out that the cosmological constant is actually finite in string theory. Not, let me just finish this slide. So it's not quartically divergent as you would have expected in field theory. It's actually finite, even without Susie. I'm not assuming Susie anywhere in this talk. Yeah, question.
So by tree level, you mean the sphere diagram?
Yeah, I do. So at least to this order, the one loop diagram and the sphere together, if you wish, because it's 0, by conformal invariance, which I haven't talked about, you get a cosmological constant, which is finite in string theory. This is an old result. It's new to maybe the field theorists, but the string theorists know it very well. All right. Now, of course, modular invariance severely constrains the spectrum of states at all mass levels, as it has to, because we're demanding some symmetries on the partition function, especially this inversion symmetry. Now, the partition function, remember, is the sum, and there's the spectrum, there's the masses. So in order for it to have a symmetry under t to minus t, there's got to be some weird thing going on with the spectrum in order to do this. In general, to solve this problem, demand this and find out what spectrum of states is allowed. Very complicated math problem. You need to exploit properties of sequences of products of Poisson resummations. There are numerous, this is really modular function theory is a branch of mathematics connected to a branch called number theory. And there are insights that you can gain from various methods that were developed by Hardy and Ramanujan in 1917. And of course, if you're in a SUSY theory, then z equals 0 is a solution, of course, that happens when you have supersymmetry. But otherwise, what happens? So this is something I actually studied, I don't know, 26, 27 years ago. It's amazing how time flies. And what you find is something that I called misaligned supersymmetry, which is that in any tachyon-free closed string theory, it turns out that spacetime SUSY can be broken, but a residual misaligned SUSY must always remain in the spin spectrum. In other words, imagine you have a bosonic sector, and it contributes some number of states. I'm counting number of bosons and minus number of fermions, so the fermions are plotted negatively, boson numbers are positive. If the states are aligned, these cancel that, this cancels this. If they're aligned, meaning that n is even for both. But then if I shift the fermionic sector over to the odds, I'm shifting them down. And what's happening is that I preserve always in string theory the functional form, but the number of states keeps changing as I do this, but always the functional forms cancel. And so it's a misaligned supersymmetry. You don't see it. It's a number of bosons, a bigger number of fermions, an even bigger number of bosons, an even bigger number of fermions. It oscillates. But what's canceling is the functional forms. In actual string models, you can actually see how this happens. It's really remarkable. You always have these functional forms. They always cancel. It always looks like this. There's not an asymptotic supersymmetry. Sometimes people talk about that as you go to infinity, the number of bosons and fermions becomes equal and the difference goes to 0. No, this is what happens. Okay, so we've thus far seen that the strip region S is infinitely larger than the F region, and we know how to relate them. But is there a corresponding way to relate the integrals? Is there a way to extract the infinity, in other words, and thereby evaluate them? This would provide a precise way of expressing string theory amplitudes in field theory terms. Now, this is actually remarkable. Let's concentrate on situations where the F integral is finite. The corresponding strip is still an infinite number of copies of that, so it'll diverge. But it turns out, is David here? David, kudos up. He might start remembering some things here. There's a result due to Rankin and Selberg, mathematicians in the late 30s and early 40s, who proved that you take the string integral, and that's what the strip integral, this is what it is. You deform the power of tau2 a little bit, and then take a residue. This is still divergent, but you take the residue, and the residue is the string amplitude. So the finite string amplitude can be expressed as the residue of a divergent deformed field theory amplitude at a pole in the complex S plane. This is valuable because you can now express this thing in terms of only physical states, the ones that have field theory analogs, and just take a residue, which will give you, again, just a trace over field theory states. I can change this by doing an inverse Mellin transform in the complex plane to a slightly different formulation. And this was first written down by mathematicians in 1981, and David and Nadi in 1991 also introduced this into the physics community. So David, you remember this, I know. Okay, so this is a very powerful result, and we're going to use it a lot. Because what it does is it takes a full string amplitude, which depends on all the states in the spectrum, both the physical ones and the unphysical ones, and relates it to just the physical states. And so it enables us to express string theory amplitudes in terms of supertraces only over physical states, the things that have field theory limits. And this will also allow us to rigorously extract EFTs from string theory and analyze their properties. Okay, so we can do this with the cosmological constant. We can just take that unknown integrand f, take it to be the partition function itself, and we find that the supertrace of 1 actually vanishes, meaning numbers of boson minus numbers of fermions in this oscillating way still somehow, when you regulate it correctly, comes to 0. And this finite cosmological constant, which is finite, already that was the miracle, but now I'm telling you that there's an even bigger miracle, that you can express it, and this was work done in 1995, as the supertrace of the m squareds over that oscillating spectrum. Now, this is very different from field theory. In field theory, you would say the supertrace of 1 governs the quartic divergence of lambda, and supertrace of m squared governs the quadratic divergence of lambda. But here we're saying something very different. This is completely stringy. This is finite and can be written like that. And the way that these are satisfied is by this oscillating. Okay, Higgs mass. So how can we use this technology? Again, I'm going to restrict my attention to these same classes of strings. We're not trying to do this in a particular model. Our goal is to be doing this in a framework. So Jeff asked a question at the beginning. I'm now going to give the answer. For us, Higgs means any scalar field sitting at the minimum of a potential whose VEV affects the masses of particles in the spin spectrum, regardless of the gauge symmetries it may break. So that includes the standard model Higgs, but also includes other kinds of Higgses and moduli. Okay. So our interest is in calculating the Higgs mass, not in studying the Higgsing phenomenon. So we're going to live here. How to do this in string theory, I don't know. If anybody knows of any work done on this, I would love to see it. My collaborator and I did not know of any, but we're going to just live down here, and we're just going to work in the Higgs phase and ask, when the scalar field is already at the new minimum of the potential, what are the fluctuations happening around here? Again, we're going to preserve modular invariance. So in general, the fluctuations of the Higgs around its VEV will affect the masses of the states across the string spectrum. So phi is going to denote the fluctuation of the Higgs around its VEV. And for any state, we're going to say there's going to be some shift in the masses. The left moving mass will shift by some amount. The right moving mass will shift for some amount. And this will happen for every state S. Now, not all masses are affected, only the masses of those states which couple to the Higgs field. So where am I putting in the information about what Higgs field I'm talking about? Right here, by saying when are these 0 and when are these aren't 0, but I'll just study it in general. Okay, that's what I'm dealing with all at once. Modular invariance does tell me, however, that the shift to the left for any state has to be equal to the shift for the right. Otherwise, the fluctuation would break that symmetry as tau goes to tau plus 1. So the one loop effective potential now becomes phi dependent, because in this partition function, I now have to take my masses that were in the exponentials here, and they are also become functions of phi. And then what I do is I would just calculate the curvature at the bottom, and that's the second derivative. Okay, so here was the partition function. I want to calculate its second derivative. Well, there's a tau 2 part and a tau 1 part. This just depends on the masses. That gets shifts with phi because of the fluctuations, but the mass left minus mass right doesn't be any phi dependence, because modular invariance restricted the shift to the left to equal the shifts to the right. So this is equivalent to an insertion, which takes this form when you work it out. And so this is just an insertion into the summand. Only depends on the total mass and only on tau 2, very important. All right, so when I truncate to phi equals 0, we therefore have the insertion has a tau 2 times something and a tau 2 squared times something. And here's what the somethings are. And therefore, what I'm saying then is that the Higgs mass in general in string theory is just going to be the complete string amplitude, meaning the complete integral with the insertion of this tau 2 times something and tau 2 squared times something. So are we done? We just have to calculate those x's? No. Because it turns out that these x insertions into the partition function sums break modular invariance. And this actually happens because of a rather subtle modular anomaly. Now, it turns out, therefore, that proper modular invariance can only be restored through the addition of an extra term. I just have to add it. You can call it a modular completion. It's needed to complete a certain square. I really can't get in. This is where I have to be a little bit of an expert on modular function theory. For those of you that do know it, you can ask me during the questions, and I have a little lecture, but basically there's a reason I have to add it. But I can interpret it for everybody. The X terms capture the effects of the mass shifts induced by the fluctuations of the Higgs fields. However, in string theory, there's also going to be gravitational back reactions, specifically deformations of the moduli fields arising from these fluctuations. And those can also make contributions to the Higgs mass. So these contributions should be universal, independent of the X insertions. And modular invariance has actually given us these extra terms. So I could have calculated them by studying back reactions, but I knew by modular invariance exactly what term this had to be, and that's what it is. And the C there is a model-dependent thing about how the Higgs is embedded, say, in the string theory, in the lattice, or whatever I'm dealing with. All right, so I have to insert this there. Modular invariance told me that, but that's very important because I recognize this extra term. This is just a constant. And so modular invariance, when I insert this constant, what is this? This is no insertion. This is the same thing as saying the cosmological constant. So this gives me a cosmological constant. So what I'm telling you is that the Higgs mass actually depends on not only the X insertions, but the cosmological constant. And that's really remarkable because in field theory, you would not have expected to have a relation that involves a cosmological constant. The zero of energy in field theory is not knowable. Only a theory of gravity can ever depend on this. But in string theory, we get exactly this. Remember, in string theory, this is finite. This is something that can be added like this, and it comes out. These are the two quantities that are the heart of most hierarchy problems that people worry about. And here they are related in a very interesting way in string theory.
Quick question?
Keith?
Yeah, please interrupt.
So the lambda here is a function of the moduli, though, right?
It is. I'm assuming I have a stabilized string vacuum, obviously. I asserted that there were no tachyons. I should assert that there are no other, yes. I'm also assuming when I calculate this phi that I'm at a minimum, which means that I am demanding that the first phi derivative vanish. Okay. So far, I've now told you how to calculate the Higgs mass for any string vacuum and any Higgs scalar therein. I just calculate my X insertions for each state. That's where I decide which state I'm talking about, which scalar I'm talking about. I calculate the one loop cosmological constant, which is just summing over all the states. And then I calculate this quantity. And there it is. Of course, what am I calculating? The lambda and also the bracket. The bracket is the full modular integral, which includes physical and unphysical states. Now you can ask, is this Higgs mass, this expression, divergent? Well, you can look at how this behaves. Again, we are assuming that lambda is not having tachyons, and we're in the IR representation, so the only surviving contributions with the integrand are those that are level matched. And so I look here at the light guys, and I see that only massless states could ever matter. And then I ask myself, well, which ones? I've got a tau 1 in the beginning to the -1 in the partition function. This term, when I insert it here, will give me a tau 2 to the -1. This is a tau 2 to the 1. That gives me a constant, whereas this term gives me an overall power. So this is how f, the modular function, the integrand, goes in the limit. And then when I'm integrating over d2 over tau 2 squared, this term is finite. This gives me a logarithmic divergence. So the Higgs mass is at most logarithmically divergent, only if the C1 contribution here, only if there are massless X2 charged massless string states. If there are, then the Higgs mass can be logarithmically divergent. Otherwise, it too is finite in string theory. Interesting. That's already remarkable because we not only find that the cosmological constant is finite, but the Higgs mass is probably finite or has a logarithmic divergence at most. But it's still divergent, so we have to find a way to regulate. This will allow us to isolate the divergences and extract finite results. And if it becomes regulated, then it's finite, and then I can use the Rankin-Selberg techniques to express these amplitudes in terms of only physical states at all mass levels, just like lambda. And that will allow us to extract an EFT description of the Higgs mass and study how it runs. Okay. Now, many different regulators are possible. Now, remember, this is the X2 charged massless states that are causing the problem. Well, you could remove them, their contributions, and handle them separately. This is the approach that Kaplanowski took in 1987 when he wrote a classic paper basically beginning to create a formalism for calculating not Higgs masses, but string threshold corrections for gauge couplings, where there were similar logarithmic divergences. Just subtract them. Another possible answer is remove the divergence from the dangerous regions of F. For example, for integrands which diverge like that, up as tau2 goes to infinity, put a cutoff in, some t regularization parameter, don't integrate beyond there. So as you take t to infinity, you remove the regulator, but otherwise it's there. And then it's a parameter in your regularized finite quantity, and you integrate over the whole fundamental domain up to tau for this part. But then when you are going beyond that t and doing this part up here, subtract away the part that gives the divergence. That's the recipe. Zagier actually worked this out. And then you do the whole unfolding Rankin-Selberg theorem, and you find that you get what you would expect, but you get another term in addition, and it has a logarithmic dependence on t, as you would expect, and indeed it comes out that way. Modular function theorists already proved this. Note this looks like an RGE for an EFT running, for IFT, with t interpreted as a renormalization scale mu. In fact, you would be tempted to make this identification. And that's a completely reasonable thing to do, and we're always going to do it. Wherever there's a cutoff, I'm going to define that to be a running scale. Okay, now it's not an accident that you can identify things this way, because wherever you're suppressing things, you can decide what's heavy, what's light, and identify a scale that way. I don't have time to go through this, but you'll have my slides so you can look at them later. All right, those are two approaches to regulating, but neither one is modular invariant. You can't just remove the contributions from the massless states while leaving all the other states intact. Modular invariance mixes the states at all mass levels. You can't deform the thing by imposing a t cutoff at a certain value of tau2 either. That's very field theoretic and breaks modular invariance. The only thing I really have to do is deform my entire theory in a modular invariant way to introduce some other deformation integrand factor, a regulator function, into the integrand. And it has to have certain really nice properties. It has to be modular invariant by itself, of course, to be smooth. It has to have a straightforward interpretation. I want this to be physics, not math. I need to suppress the parallel divergences at the infrared cusp. I should have various internal parameters so that I can take a limit and get the limit when this goes back to 1, where I remove the cutoff. It should leave the rest of the theory intact as much as possible, and so forth. There are a lot of things it needs to do. And we actually, using certain results in the literature, we developed such a function. We can only construct one, interestingly, at least so far. We don't know if it's unique. I doubt that it is, but modular functions often have weird symmetries that make them unique. But either way, here it is. It has two internal parameters, rho and a. It doesn't really matter. For the experts, this is how it's defined. But don't worry about it. The important point is it has a parameter rho and a parameter a, and it goes to 1 for all tau as a goes to 0. So this is the limit where it becomes unregulated, where you remove it when a goes to 0. Otherwise, when a is bigger than 0, it decays exponentially rapidly as tau2 goes to infinity. So it's just what we want. And for certain special cases, it has direct physical interpretations. Karitzis and Kunas showed this. And it has a certain symmetry, which is going to be critical later. So what does it look like? Here is a plot of the function as a function of tau2. This is for different values of a. This is not tau1. This is a. So for any tau2, you can see that at large tau2, where the divergence would be, G drops exponentially rapidly to 0. So this is why it kills the IR divergences here. But for other values of tau2, that are not that high up in the fundamental domain, it preserves the theory. It goes to 1 very nicely. And the transition between the two over this hump, the hump region itself is climbing towards the infinity as a gets smaller and smaller, so that when a goes to 0, the whole thing is gone and it's just all sitting at 1. Preserve the theory. A plot of this, any slice through it, here's what the function looks like as a function of tau2. And it's the normal theory, it's the suppressed theory, and then there's just a little transition point here. Modular invariant is the point. This is how this works. And so we have a way to identify mu. Mu is just this rho a squared, it turns out, which is where these humps do appear. Okay, so we use our modular invariant regulator to regulate the Higgs mass. We do this. So we deform our theory by this amplitude G. And remember, we have two contributions from the X charge states and from the universal background back reactions. And because it's finite now, because we've deformed the theory, we can use Rankin-Selberg, take the residues, and express the amplitude in terms of supertraces only over physical states only. Now, the calculations are a mess, but the answers are, well, you can call that a mess if you want. Bessel functions. Here's the X contributions. Here is the cosmological constant contributions. And you see it depends. So it's this plus this quantity times this. And each script K here is an infinite sum of scaled Bessel functions. It looks like a complete mess. But if you stare at it longer and longer, you begin to see certain things. For example, you'll notice that this X contribution part depends on the supertraces of X1 or X2, massless or massive. And these are the supertraces of just the masses, or to various powers, mass squared, mass to the fourth, or mass to the zero, number of bosons minus fermions. You also notice that only certain terms contribute in the mu to zero limit, the infrared limit, as mu goes to zero, and it turns out to be this. Remarkably, this is finite. The Higgs mass running as mu goes to zero doesn't diverge. It goes to a finite number, which depends on the cosmological constant. And notice in the limit, even in the deep IR, this depended on all the states. Remember, this was supertrace of m squared? And this depends on all the states. This is not just supertrace of massive or massless. It's both added together. All states contribute, even in the deep IR. All right, you can look at how this combination of Ks, of Bessel functions looks. And this is actually, you can see what the interpretation of it is. It's the contribution of each state of mass m per unit x2 charge, the contribution to the Higgs mass. At low mu, the states are frozen out of a certain mass, but at high mu, above that mass, it produces an EFT-like running. And in between there, string theory gives you this Bessel function, which gives you a very smooth dip region and a kind of interpolation. All right, all other terms are subleading, and so when you put it all together, you get this. And this is the anatomy of the running of the Higgs mass in string theory, at least in closed strings. Here is the infrared value, which is some finite value for the Higgs mass. You then have the dip region as you go upwards. Then you enter your logarithmic. It can be power law depending on how the states add up. The KK states can turn logarithms into power laws. Then you're beyond the stage where your regulator is reliable. So you don't know what's happening here, but you have to come back down in the deep IR, in the deep UV. So you have a dual EFT region and a dual dip region, and finally a dual deep IR. Why do we have to have this duality? Because there is a scale duality. Now, I don't know if this has ever been talked about. We didn't find it in the literature, Steve or I, but you can prove it very quickly. Well, first of all, it implies that there's a maximum degree to which you can probe UV behavior. Increasing mu any further just reintroduces IR-like behavior. That's why the background colors of this plot, you're from the reds, and you're going up to the blues, the IR, it becomes UV, and then back to IR again. The theory then, has to have a vanishing slope right at the top, kind of like a vanishing beta function at the self-dual scale. And so this scale duality requires that even the deep IR, which would ordinarily only care about light states, must know about the dual deep IR up here where all states contribute. So they both have to be locked together in some way. And that's why all the states are contributing even in the deep IR. We're used to this in string theory. I would point out that the character of any partition function, Jeff will know this, the depth of the tachyon determines the Hagedorn temperature. This is the same UV-IR behavior right there. All right, why is scale duality? Because we already made a point that mu is related to the 1 over t, which is a particular value of tau. And so since tau goes to 1 over tau, that means t has to have a symmetry 1 over t, which means any identification mu has to go like that. And therefore you have to have a symmetry as t goes to 1 over t, mu has to go to 1 over mu. It's unavoidable. Same thing here. In this plot, we said, oh, look, this is a plot from tau 2 going from 1 up to infinity. But I could have plotted it all the way down to 0, and it would have the same behavior, another hump, and then back down to 0 again. And I could have chosen to identify my T cutoff with that other region instead of this region. That would have been the scale duality. Our modular invariant regulator, in other words, simultaneously regulates both the IR and the UV because they're the same. And so what you wind up with is inherent in any attempt, and I'm almost done, to extract an EFT description from a modular invariant UV-IR mixed theory is a choice of direction as to what constitutes UV, that's what you integrate out, and what constitutes IR, that's what you retain. So making such a choice in order to establish an EFT inherently breaks modular invariance. And this scale duality is thus part of a deeper structure that exposes the role of EFTs in a modular invariant UV-IR mixed theories. Remember, we started to identify the scale, the space-time scale with this rho A squared. These are the parameters of the regulator on the world sheet. And we said, okay, this is where this determines the cutoffs, where the theory starts suppressing. So we're going to identify that with mu. But once we did that, we made this identification. So for any rho A squared, we are plotting a certain value of mu. And that's the identification. But then scale duality says that if we have this mu, we also have to have the other mu, which implies another branch. And so we are forced into having two branches for identifying rho A squared, our world sheet scale, with the space-time scale mu, which leads to a four-fold symmetry here. And this relates the world sheet parameter with the space-time scale mu for any EFT. These are the EFT regions in beige, out along very far below, let's say, the string scale, much below in either direction, or the dual. And so this becomes an additional self-consistency requirement on our regulators. They have to have that symmetry. And so identifying a space-time scale corresponds to choosing an identification branch. Are we going to be on the blue? Are we going to be on the green? And these have opposite UV-IR directions. Increasing my world sheet regulator either increases or decreases the value of mu depending on which branch I'm on. That's the symmetry. So for string theory, the passage to an EFT requires choosing a spoke in this fourfold thing, because you have to choose which theory you want to work in, and you've broken the fourfold symmetry associated with modular invariance. So the rainbow plot we had before, where you started way down there and then you came up there, that corresponded to starting in this language and going up toward the middle, up here. And then this part corresponds to coming back out along either up here or up there, either spoke. And of course, I've labeled this IR, dual IR, IR, dual IR, maximum UV, but I could have just flipped UV and IR completely everywhere in this by choosing a different spoke to use my language. So it's okay. You could ask, therefore, about the role of EFTs, but I think you see my message already. It's more complicated than just saying there is an EFT down there. It is an EFT. It shows the kind of running with softened divergences, but it has all these other properties that depend on the infinite towers of states, even at light scales. So that's not what you would expect. So caution advised. Finally, an extra bonus, and I will be done. If you consider cases with no X2 charge or no net numbers of massless X2 charge states, then the Higgs mass is actually finite. In that case, it turns out that you take this mass, you reintroduce the masses are functions of phi again, then it turns out that this is the double derivative, phi derivative of that. And that means that the mass is, this first term is just the derivative of lambda plus the thing itself. You can assemble this into a covariant double phi derivative, and you can write the Higgs mass in string theory as a stringy, as a double phi derivative, a covariant, modular covariant phi derivative of what then can only be interpreted as a stringy effective potential for the Higgs mass, which means that you now have relations where you have an effective potential phi, a lambda hat, and the cosmological constant is it, truncated at phi equals 0, and the Higgs mass is its derivative, truncated, both from the same potential. And if you take mu to 0, the unregulated case, we remove the regulated, the cosmological constant, which is finite, and the Higgs mass, which is finite, are both related to the effective potential in this way. These are exact relations. They're finite. There's no divergences. These are numerical. Moreover, we previously shown that lambda could be expressed it's a finite thing. It's just the sum of the mass squareds over the spectrum, the entire spectrum. Well, now we have the corresponding result for the Higgs mass. It's the sum over all the states, again, squared. Now, you might think, well, this is not a big deal. We started, after all, by saying that this was going to be lambda, and then we're going to calculate the double derivative. But this is the full string amplitude. There was no guarantee that this structure would hold across the Rankin-Selberg transition to purely physical states. In field theory, you might have anticipated something like this, but of course, you do the Coleman-Weinberg calculation, there are divergences, there require cutoffs that change the phi behavior. This doesn't actually happen. And also Coleman-Weinberg, I want to remind you, had to eliminate certain quadratic divergences by fiat. We don't have any of that. In string theory, all these quantities are finite, the divergences are killed, and the structure is preserved. These are precise mathematical relations. And this holds as a function of the scale, and it holds even in our UVIR mixed theory in the presence of scale duality. And we also have this appearance of the modular covariant derivative. So there's a lot of other things. We are just at the tip of the iceberg here. There are other regulators, other quantities to calculate, other kinds of things we can look at. The implications of scale duality are likely to be very important. One might like to know how much this extends to open strings. And then, of course, there's the gauge hierarchy problem. And my last slide is just to point out three possible ideas. One is that using our results, you could recast the cosmological constant and the hierarchy problem in this way. So that implies that there are some new ways to think about the hierarchy problems. They look like Veltman conditions, actually. The only difference relative to Veltman is that these are supertraces over all states, not just the light ones. The second idea is that, well, you have this running and then you go into this dip. If this dip becomes tachyonic, mass squared less than 0, then you might trigger electroweak symmetry breaking that way. That would require certain relations about these supertraces. It would be interesting to find string models where that happened. But overall, takeaway message, hierarchy problems assume traditional field theory relations between UV and IR, but string theory tells us that we have UV-IR mixing and softened divergences, even finiteness and scale duality. So the hierarchy problems may not be as fundamental or survive in the manner we normally assume. So sorry I went over a little bit, but thank you very much. And I'm happy to take questions.
Thanks so much, Keith. Really fascinating. I certainly appreciate you stepping us through all of it in an understandable way. Any questions? Yes.
So in the expressions you have then, so where is the condition phi equals 0 coming from? So you would expect to be a dependence on if there is a breaking of the symmetry of the back expectation value of the fields.
I can't see, but that sounds like Carlos. Is it Carlos? Hi.
It's Carlos, yes.
How are you, Keith?
This is amazing. You hear it's all done by different senses than if you're in the room. Yeah, remember I'm working here, right? So phi are the fluctuations around this point.
Phi are the fluctuations already, but where is the dependence on well, there is no dependence on the precise value where the
You mean the VEV?
Yeah, the VEV. Yeah.
You mean this relative to this?
Right. Well, we cannot see. Sorry. Can you share the screen?
Oh, I'm not sorry. I stopped sharing. Yeah. Okay. Okay. How do I reshare? Oh, I see. Hang on. I'm still learning. One of the advantages or disadvantage of my NSF position is I no longer teach.
Oh.
I'm not used to teaching with this share screen. Here we go. Okay. Right. So, right, see it now.
Right.
So we're down in this region. Phi are the fluctuations here.
I understand, yes.
The VEV is this radius, and nothing we are going to do in here locally is going to depend on that VEV. And in fact, this process of falling, I don't honestly think it's been studied in string theory. And Steve and I, my collaborator Steve Abel, and I tried to think about this for a month. We wasted a lot. I don't want to say waste. Nothing's a waste, but we spent a lot of time on it. The problem is it's not a simple symmetry breaking because it is rank cutting. If you think about SU2 cross U1 goes to U1, that is a rank cutting symmetry breaking. And rank cutting gauge symmetry breakings are rather tricky to do in a continuous way. In string theory, most of the time people construct, models and they do a symmetry breaking, it happens through an orbital folding, which is a discrete other mechanism. And people sometimes say you're in the Higgs phase, but to actually have a potential, like we're talking about here, and do this rolling, I don't know if the technology has been developed to understand this. If anybody knows of any reference, please let me know. So fortunately, we could do the calculation because our question was only not about the Higgs VEV, it was about the Higgs mass. And so we were limited to being locally down in here. And that was good because that's what we had control over. So if you will, those Bessel functions were describing the shape down here.
Okay, very good. Thank you.
Let's go to John, John Rosner, who has a question, and then we'll come
Hi.
back. Oh, John, you're muted.
You're muted, John.
There we go. Oh, hi, Keith.
Hey,
Hi.
hello.
You mentioned that the Higgs was mixed. Is there a measurement that would tell you how much mixing you actually have?
What way do you mean mixed? I didn't say the Higgs was mixed. I was talking about UV being mixed with IR. UV-IR mixing. I'm not talking about the Higgs state being mixed with anything. Of course, it will have to couple to a lot of stuff to do its job. Did you mean mixing in some other way?
No, I misunderstood. So it's coupling to all the known particles. It's standard.
It is this. I'm not in any particular vacuum, any particular model, so I don't know what it is. I'm just telling you a general procedure to calculate it. You would calculate how much mass shifting there is throughout the spectrum, and that determines what symmetries you break and what these couples to. You would, as a first step in any phenomenological analysis, because you want to know what the Higgs couples to, what scattering can occur, and so forth, right? But these are very simple questions. You would have thought this talk that I gave could have been given 25 years ago. And surprisingly, string phenomenologists have not thought in a global way about symmetries like modular invariance very much. And I've been on a warpath for 25 years to get them to think that way, because I think that there's a lot of stringy wonderfulness lurking there. That phenomena that string theorists know all about. Dualities, my God, they've been doing for years and years, but it hasn't percolated into the phenomenology community in the ways I think it should. And I think we better think about hierarchy problems in a fresh new way, because the LHC is suggesting that we might want to think that way.
Thank you. Aurora.
Hi. Disclaimer, field theorist here. So when you were calculating the x's, you had to introduce the cosmological constant because of a modular anomaly. I was just wondering how you're using anomaly here. Like, what sense is it in anomaly?
Oh, good. You just got me to be able to present that sheet.
You're welcome.
In spite of what you might have thought, that is not a snapshot from the paper. It would have been 2 or 3 pages in the paper. I really wrote this out simply for embedding it very succinctly. I don't know that I can go through it in detail if you're a field theorist, but let me just convey the idea that the insertions, can you see this all?
Yeah.
Okay, these X insertions, when you do these sums, don't worry about Q. Q is just a clever way of writing this exponential factor with the tau up there. The Boltzmann factor, this is what this is, basically. The Q insertion can be realized by taking a tau derivative of that. It just brings down an extra factor of the Q, that's the insertion. So these X's, which are like these Q's, these charges, I'm in something called the lattice formulation here, it doesn't matter. The point is that the X's correspond to tau derivatives. So you'd think everything is okay, but the problem is that the tau derivative is not covariant. And this is just something that is well known in modular function theory, and they call that an anomaly. And so I'm using the same words here. Basically, a modular function, remember I said that when I go from tau to a tau plus b over c tau plus d, I get back to the same thing? Well, a modular function, I'm just telling you something in mathematics now, A modular function is any function for which that's true up to a factor like this, which is like it's like a coefficient that comes along. And the k power here is called the weight of the modular function that this is. And this is a subject that, people have been studying for 2 centuries, and Ramanujan filled notebooks on these things. These are modular functions. There's another class of functions called mock modular functions, and you have the world expert on that sitting in your audience right there. But the point is, take a tau derivative of this on both sides. You find that you get back another modular function with a slightly higher weight, but then there's another term. And that extra term is not supposed to be there. It's not expected. They call this an anomaly. And the way to restore the theory, to fix it, is to say, well, that's because my tau derivative wasn't covariant. And my real covariant tau derivative, engage symmetry. It's you have your derivative, but then you have your connection term, right? Or in general relativity, you have a connection term. This is like a connection term. The true tau derivative is the tau derivative itself plus the connection term. Connection term has another power of tau 2 downstairs. So really, the physics, if you do all the calculations in string theory correctly, including gravitational back reactions, you will automatically find that your derivatives take this form. You'll get this from one side, this from another calculation, and they will combine to make perfect modular symmetry. There's no anomaly that you can't get around. I'm just saying, if you only looked at one half of the theory, you would think you had an anomaly, and there's another gravitational part that gives you the other part to build a modular covariant derivative. And now here's the thing. When I combine these to make my full left moving and right moving part, I get these 2 derivatives, and I have to multiply by a tau 2 squared. Don't worry about it. But you can see what happens now. My charges, my derivatives, I get the diagonal here, and I get the off diagonal from each of these. But then there's the constant term. Remember, I'm multiplying by tau 2 squared. That cancels the tau 2 squared here. And it comes out like a constant. What I'm saying is I got this part by calculating. I got this part by direct calculating. These depend on the insertions. But then there was this gravitational back reaction, which gave me this extra piece, and that's from the anomaly. And when I do it, I build the perfect square.
But the point is, we shouldn't be thinking about chiral fermions.
What?
We shouldn't have in mind chiral fermions coming in.
No. That's a chiral. No, that's an anomaly for another symmetry entirely.
Okay, good. I think that was part of the question.
Oh, thank you. No, that's an axiom. That's
part of my question. It's not.
No, that's great. That's an axial anomaly. This is an anomaly of the modular symmetry.
I see. Yes, and so.
Thank you.
Keith, two questions. One's kind of vague, which is, if I didn't know about modular invariance, is there a space-time argument that would tell me I need something like misaligned SUSY? Like, could you have explained it to a field theorist without knowing anything about a string theory modular invariance statement?
All right. Misaligned SUSY is something I kind of came across 27 years ago, and I have been explaining it forever to different audiences. And the purpose of this talk was not to talk about it. It was one slide, and it's just part of the stream of consciousness here, but it wasn't the main point of this talk. But if you wanted to ask, how can string theories be finite? Not string theory. If you want to ask, how can field theory be finite? And ask for other ways to have finiteness in field theory. If you're willing to allow an infinite tower of states, that's all. You don't have to make it string theory. You don't even have to ask that they come from excitations of a fundamental string. You could just say, an infinite tower of states, go play with it. I actually had a paper, April 2001. If you want to look it up, April 2001, I wrote something that looks like a colloquium. I actually used to give it as a colloquium, in which I derived misaligned supersymmetry from field theory. I motivated it. Basically, what I did was I asked, if in field theory, the divergences that we know from the Higgs mass and the cosmological constant if those divergences are expressible in terms of supertraces, and that's field-theoretic, that statement, then how can I cancel supertraces without supersymmetry? Are there other configurations that do it? And you can ask that question. And if there's a finite number of states in your theory, it turns out you can't. You got to pair them up one by one, and that makes supersymmetry. That's the SUSY solution. But if there's an infinite tower of states, there are other solutions you can write down. And that's the misaligned supersymmetry. So how do you like that? Does that answer your question?
Yeah, that's the kind of argument I was looking for. Is there a sense in which it's unique? Like this, it had to be this way, or?
I think it had to be that way. I think it had to be that way. It's the only other way that string theory can have an out. You see, well, first of all, let me say that it had to be because I proved it, okay? So mathematically, I mean, this is an old 1994, you know, it was proven. So misaligned is the consequence of modular invariance. It had to come out that way. But I can't think of any other way it could have been if you want to preserve certain properties that you know. You want bosonic states to have degeneracies that grow exponentially with mass. You want fermionic states to have degeneracies that grow exponentially with mass. And you want to have finite supertraces. I don't think there's any other way to do it. Anyway, the paper I was talking about in 2001, here, it's this one. This is written for the field theorists.
Good.
And in fact, you will find the beginnings of this talk in here. The strip, the fundamental domain in here.
Very good. I think the other question I had was slightly more technical, which is that your regulator G tau, that was decaying exponentially when tau 2 got big.
Yep.
Is it the cusp form? Does it decay exponentially as tau 2 gets small as well, or?
If tau 2 goes to 0, it certainly does because it's a modular invariant function. So what it does over there, it has to do over there.
So it is a cusp form that you.
I believe so.
Okay. Very good.
It's a beautiful function. Here is what it is. Since you're asking, I'll make a point. All right, here is what it is.
You had it in terms of the, yeah, there it is, yeah.
All right, so you start with the circle partition function where A is the inverse radius. You then take that circle function and the circle function with rho times that radius. The other parameter is rho. You take the difference, you differentiate with respect to the radius, you multiply by all of that. Seems like a funny thing to do, but it has all the right properties and all the right symmetries. Ritzis and Kunas found this structure sitting in their integrands when they replaced the background conformal field theory with 4D time with an SU2 level K Weston-Witten model. When they did that, they found that that was the effect. They were doing it as a regulator, a different way to regulate the theory in a modular invariant way. They changed the conformal field theory, which is what I'm effectively doing. Here's the difference. We did not do that. We added some extra piece. This factor that we added was very important because what it did is it gave us an invariance under this goes to 1 over that, which they did not have. Why do we need that? Because remember, this is going to become my mu. And so the only way to even have a way to interpret this in space-time is if I have an invariance under this symmetry. So this is another condition on a regulator in string theory, which we are imposing. That was not, I don't think, appreciated before. If you want a regulator for which you are going to then identify a space-time scale mu and try to write an EFT in a running of a quantity, if you're going to do that, then your regulator had better have all the symmetries where the parameter should have all the symmetries that you're going to identify with mu should have all the symmetries that mu has. And this is a symmetry. So that's why I say this will be critical.
It's weird. I was sort of looking at something similar for some totally different reason.
Uh-huh.
All connected to this. Some bootstrap reason, which
Oh, yeah.
in which it was natural to differentiate with respect to the modulus.
Yes.
It's peculiar.
Well, the bootstrap stuff is really elegant in a lot of ways.
Very nice. Thank you.
I want you to know this is the first string talk I've given in more than 15 years. I've been doing dark matter and cosmology all this time. Nice to come back.
Yeah, a stunning return to form. Sangu, I think.
Let me ask after, I guess, because it's getting too delayed. I'm happy to ask offline.
Oh, sure. Any other questions?
No, who was that? Who was that with the questions offline?
Samu, I want to ask
Oh, okay.
at least 2 questions.
Oh, no problem. Seth, do you want a copy of the slides?
Yeah, that'd be great if you could send them to me.
Yeah.
I will email them to you. Is this talk, the talk was recorded?
Yes, and if you don't mind, we'll put it up. Well, we already had an extensive discussion about putting it on YouTube.
So I hope your group mates don't know the horrors I put you through about that.
No, sensible suggestions you had. But let me stop the recording and then we can continue with some.
Great.